All right. So we have completed studying a few examples on spatial kinds of discrete random variables. Now we are going to do the same for continuous random variables. There are a large list of spatial continuous random variables which can be classified according to their probability density functions. Remember now, a continuous random variable is a random variable which can take uncountably many possible values over the real line, and they are modeled with their probability density functions. And the list of spatial continuous random variables that we are going to study are continuous uniform random variables, exponential random variables, and normal random variables. The second item here, exponential random variable, is actually closely related to one of the discrete random variables, which is Poisson random variable. And they both have a high essence in our future studies in simulation course. Whereas normal random variable is going to provide us an important basis and a key to move forward in statistical analysis course. So we are going to give information about these three random variables. Then we are also going to name other types of spatial continuous random variables, which you can hear about in your future courses. So even if these random variables are not going to be covered in the contents of this course, it is best to at least learn their names so we can know about them in our future studies. So in this section, we are going to learn about some common types of continuous random variables. And usually, many measurable random values in real life can be modeled with the following random variables. So for example, what do we mean with a measurable random value? For example, the completion time of a race. So it depends on the people who are racing actually. So the completion time of race is a random value. We cannot be sure about it until the race ends. So we can model such a measurable quantity with a continuous random variable because time itself, it's not countable. It's only a variable that is measurable. Or for example, the birth weight of babies, okay? So the birth weight can be measured in kilograms or other type of weight units, okay? And it's again a random quantity and it is continuous. So in real life, such measurable quantities can be modeled with continuous random variables, and we call these classes of continuous random variables spatial continuous random variables because they can be classified according to their probability density functions. And we are going to start with the simplest of these continuous random variables, which is the continuous uniform random variable. We especially emphasize the adjective continuous in front of the uniform because there's also a discrete counterpart of this uniform random variable. So even if we do not use a continuous adjective, let me remind you that whenever we mention about the uniform random variable, we by default need to imagine a continuous uniform random variable. So what is a continuous uniform random variable? Just like every continuous random variables, it is going to have a PDF. And its PDF is going to be defined in this form, okay? So we say that this continuous uniform random variable can take any real value between alpha and beta, where alpha is the lower bound of the values that this random variable can take, and beta is the upper bound of the values that it can take. And within this interval, any real value has the same chance as the others, okay? Because of that reason, we say that the density function of a continuous uniform random variable must be a constant value independent of the x value. And because an important property of the probability density function is that the area under the PDF probability density function will always be equal to 1, the area of this rectangular region should be equal to 1. This means the constant probability density function value between alpha and beta must be equal to 1 over beta minus alpha. So the area of the rectangle can be equal to 1. So we say that the PDF of a continuous uniform random variable is equal to 1 over beta minus alpha if the x value stays between alpha and beta. And anywhere else, the PDF is equal to 0. Okay? So we have said that this must be a PDF because the area under the rectangular part is equal to 1. And in fact, we can prove it by taking the integral of the PDF between alpha and beta. And the integral of a constant value is basically that constant value multiplied by x if your integral operator is x. And if you plug in the boundaries in place of x, you will get beta minus alpha over beta minus alpha, which is going to be equal to 1. So the probability density function of a continuous random variable is as simple as this. Now, an important property of the continuous uniform random variable that its PDF is constant over the values that the random variable can take. So this means the random variable is equally likely to get any real value between alpha and beta, and there are uncountably many values between alpha and beta if we consider real numbers. And alpha value is called the lower bound and beta is called the upper bound parameter, which means if we can change alpha and beta as long as alpha stays less than beta. And for every alpha and beta value assignment, we get a different uniform random variable. And if we choose alpha to be equal to 0 and beta to be equal to 1, in that case, the resulting continuous uniform random variable is called a standard uniform random variable. So with this parameter setting, with this parameter assignment, we say that this is going to be a standard uniform random variable. In other words, a standard uniform random variable is a continuous uniform random variable, which can get any value between 0 and 1. And in that case, because the density function is equal to 1 over beta minus alpha, and alpha and beta are assigned respectively as 0 and 1, the standard uniform random variable's PDF is simply going to be equal to 1. And the fact that x is continuous uniformly distributed between alpha and beta is expressed in this form. We say x is uniformly distributed with lower bound parameter alpha and upper bound parameter beta. As you can see, there are two parameters of a continuous uniform random variable. And if we arbitrarily choose any two real values, a and b, within the interval alpha and beta such that a is going to be less than b, the probability that the continuous uniform random variable x to take any value within this interval is actually proportional to this interval's length compared to the total length of the random variable domain. So probability of x being within the interval a and b is the integral of the PDF function, which is 1 over beta minus alpha, with respect to the boundaries a and b. And as you take the integral of a constant value, you get x over beta minus alpha. And if you just plug in these b and a values, you will calculate the probability of our random variable being within this interval. So as you can see, this probability is a ratio between the length of the interval that we are considering and the length of the random variable domain. Now, we are interested in computing the CDF, cumulative distribution function of our random variable. Okay, so we say that there is a uniform random variable that has lower bound alpha and upper bound beta, and we arbitrarily choose a value x within this interval. The cumulative distribution function is simply the probability of this random variable to be less than or equal to x, and the cumulative distribution function, as you remember, is represented with capital F. So capital F of x, the probability of our random variable being less than or equal to an arbitrary value within this interval, is the integral of the PDF from the lower bound parameter to the x value. And the integral here with the integral operator dt is getting out as t over beta minus alpha. And if we plug in x and alpha values, you are going to get a linear function that is x minus alpha divided by beta minus alpha. So the CDF is computed as follows. The probability of a continuous uniform random variable to be less than or equal to x is equal to 0 if you choose an x that is less than or equal to alpha, because it is impossible to get any value that is less than alpha. The alpha basically forms a lower bound for the possible values of this random variable. However, if you choose an arbitrary value between alpha and beta, that is x, the CDF value is going to be x minus alpha and beta minus alpha, which is going to be a linear function. And this linear function is going to reach to value of 1 if you take the limit as you get close to beta. Because if x is equal to beta, you are going to get the ratio to be equal to 1. Because of that reason, the total area under the PDF will be accumulated at this point, and for every value that is greater than beta, the cumulative distribution function, or the probability of a random variable to be less than or equal to that value, will always be 1. So if we check the probability density function again, as you can see, as we move from this direction to this direction, the total area under the PDF stays 0 up to this point, and starting from this point, it is going to increase at a constant rate because the PDF is constant, and the area on the left-hand side is going to accumulate to the value of 1 linearly, and from this point, even if you move further, the total accumulated area will not change. Therefore, the cumulative distribution function should have such a form. Because if you remember, a cumulative distribution function is simply calculated as the integral of the probability density function. So let us solve a question at this point. We say that buses arrive at a specified stop at 15-minute intervals starting at 7 a.m. In other words, they arrive at 7, 7:15, 7:30, 7:45, and so on. Now, please recognize at this point that time is a measurable value. So if a bus arrives at 7, then this does not mean it is going to exactly arrive at 7. So it is possible that at any time between 7 and 8, it can arrive at any time, okay? So we say that continuous random variables can take any value over the domain that they are being defined. So do not please focus on the beginning of the minutes only. Remember now, time is a continuously measured unit. Okay, so we say that if a passenger arrives at the stop at a time that is uniformly distributed between 7 and 7:30. So a passenger arrives at a time between this interval. So within this 30 minutes interval, it arrives at any time. So this is continuously distributed between 7 and 7:30. So this does not mean that the passenger is going to arrive in the beginning of the minute. So he or she can arrive within any minute, at any second, and at any millisecond. Okay, so the arrival time of this passenger is continuously distributed between 7 and 7:30. Now we are being asked this probability. Find the probability that she waits less than 5 minutes for a bus. So what is the probability that this passenger waits less than 5 minutes for a bus? Now, if this passenger is going to wait less than 5 minutes, then this passenger must arrive either between 10 past 7, or 15 past 7, or Another interval that the passenger can arrive is 25 past 7 and 30 past 7. So we are interested in finding the probability that the passenger arrives within these time intervals. So let us assume that the arrival time of the passenger is uniformly distributed, and this uniform distribution has the lower bound parameter of 0 and the upper bound parameter of 40 if we assume that the origin point 0 corresponds to 7 a.m. The start of the day is 7 a.m. So the passenger basically arrives at any time within this interval. And then he or she can arrive continuously within this interval. Now, as we have stated, if the passenger will have to wait less than 5 minutes, the passenger must arrive either between 7:10 and 7:15, or 7:25 or 7:30. So this means we are interested in finding the probability of X either being within this interval or within this interval. So because these are disjoint intervals between 0 and 30, we are going to calculate the probability of our random variable being in these intervals separately. So this means we are going to calculate the integral of the PDF function, which is 1 over 30, because the upper bound and the lower bound parameters are respectively 30 and 0. The density function is going to be 1 over 30. And we are going to calculate the integrals with respect to the boundaries that are defined here. And both intervals will have the same probability. Why? Because they have the same length. Continuous uniform random variable, because its density function is constant, is going to yield same probabilities with same length of intervals within the random variable domain. Now, the summation of these two probabilities is 1 over 30. So this means if the passenger arrives at any time that is continuously uniformly distributed between 0 and 30, the probability that the passenger will have to wait less than 5 minutes is 1 over 3. Now, if we look back and check the second part of the question says that find the probability that the passenger waits more than 7 minutes for a bus. So if the passenger is going to wait more than 7 minutes for a bus, either the passenger must arrive between 7 and 7:08 or between 7:15 and 7:23. So if the passenger arrives within this interval, then the passenger will have to wait more than 7 minutes. Okay? So remember now, you may ask this question. You may say that, so if the passenger arrives at 7:15, the bus is also arriving at 7:15. However, this is a very, very unlikely probability to exactly arrive at a certain time. Remember, for continuous random variables, we say that the points, exact points, will not have any probability, will have zero probability. Only intervals will have probability. So if we assume that the passenger arrives between the 15th minute and the 23rd minute, if we do not include the boundaries, the probability will be the same. So the probability of our random variable being either in this interval or this interval will be calculated with separate probabilities by taking the integral of the probability density function, which is constant at 1 over 30, with respect to these boundaries. And in both cases, we are going to get 8 over 30 as the probability because the length of these two intervals are the same. Therefore, the probability is going to be equal to 8 over 15. Now, let us calculate the expected value of the continuous uniform random variable that has the lower bound parameter alpha and upper bound parameter beta. The expected value of a continuous random variable is computed with this formulation. We integrate the product of the x and the probability density function within the whole real number set. So this is the general definition of the expected value. However, the probability density function of a continuous uniform random variable will only be positive within the alpha and beta interval. Therefore, we can limit this integral within the alpha and beta interval because it is going to yield a zero value. The integrand is going to yield a zero value at anywhere else. So we integrate the PDF function 1 over beta minus alpha multiplied with x within this domain, and the integral is x squared over 2 times beta minus alpha. And when you plug in the values, you will get beta squared minus alpha squared, which can be expressed as beta minus alpha times beta plus alpha. So if you express the difference between square of two terms like this, the beta minus alpha here and the one in the denominator will cancel out, and obviously you will see that the expected value is going to be alpha plus beta over 2, which is the just middle point between alpha and beta. So it is obvious, right? Because if you look back here, the probability density function, because all values have equal chances, all real values between alpha and beta have equal chances, the expected value or the average value that we are going to observe from the realization of this random variable will just be in the middle, which is alpha plus beta over 2. So now it's time to compute the variance of the continuous uniform random variable. Now, remember, in order to compute the variance of a random variable, we first compute expected value of x squared, then we subtract the square of expectation from this, and we get the variance. So this is the convenient formula for the variance. So let's start by calculating the expected value of x squared. So in order to do that, we multiply the probability density function with x squared and integrate this product over the real numbers. However, as previously said, the PDF does not take positive values except the alpha beta interval. So we calculate this integral only within this interval. And the PDF is 1 over beta minus alpha multiplied by x squared. The integral will be x to the power 3 over 3 times beta minus alpha. And if you plug in the boundaries, you will get beta to the power 3 minus alpha to the power 3 divided by 3 times beta minus alpha. So the difference of these cubic terms can be expressed as beta minus alpha times alpha squared plus beta squared plus alpha beta. So beta minus alpha will cancel out, and expected value of x squared will be computed as this function. Now, in order to compute the variance, remember, we need to subtract the square of the expectation from this function. So what we are doing here is exactly that. So we subtract the square of the expectation, and the expectation was alpha plus beta over 2. And after some algebra here, after some computation, so you can practice this at home later, you will end up with this simple form, which is beta minus alpha to the power 2 divided by 12. So square of the length of the random variable's domain divided by 12 will be the variance of the random variable. Obviously, you can see if the domain length is increased, which means if the length of alpha beta interval, the difference between the upper bound and the lower bound parameters is large, the variance is going to be large. So let's solve another question. Suppose the daily demand to milk in a dairy farm is uniformly distributed between 50 liters and 150 liters. So obviously, the daily demand to milk will be a continuous random variable because it is something measurable, not countable. So you cannot count the amount of milk. You can only measure it. So a measurable quantity must be continuously distributed if it is a random variable. So we say that it is continuously and uniformly distributed between 50 liters and 150 liters. So this means on any day, the total demand observed to milk can take any real value between 50 liters and 150 liters. The first part of the question states the probability that the daily demand to be between 80 and 120 liters. So what is this probability? So as you can see, both 80 and 120 is defined within this interval, 50 and 150. And obviously, this corresponding probability must be proportional to the length of this interval. Okay, so we are going to check about it in the next page. Then we are supposed to calculate the expected daily demand and the variance of the daily demand. And the final question is actually a conditional probability question. It says that it is known that today's milk demand was no more than 110 liters. So some observer told us in the end of the day that today's demand was less than or equal to 110 liters. Then, given this partial information, what is the probability that it was more than 85 liters? So we are going to solve each of these questions. So let's start by modeling the daily demand to milk. We say that it is modeled with a continuous random variable, and according to the question, it must be uniformly distributed. So we say that the daily demand to milk on any day is uniformly distributed with lower bound parameter 50 and upper bound parameter 150. Now let's solve question part by part. The first part asks us this: what is the probability of our random variable being between 80 and 120 liters? So we can solve this question either by integrating the PDF, which is 1 over beta minus alpha, with boundaries 80 and 120. And in that case, the integral will be x over 100, and plugged in values will yield you a 0.4 probability. Or we can use directly the cumulative distribution function. The probability of this random variable to be within this interval is the difference of the CDF values of these values. Okay? So we are going to check the difference between the CDF values at 120 and 80. And remember, the CDF function was x minus alpha divided by beta minus alpha. And beta is 150, alpha is 50, and here x is 120. And respectively, if you plug in 80 into the CDF value function, you will get 80 minus 50 over 150 minus 50. And this part will correspond to a 0.7, and this part will correspond to a 0.3, and the difference will be 0.4. In the second part, the expected value of the daily demand is being asked. And the expected value is basically alpha plus beta over 2 for a continuous uniform random variable. That is going to be 100, which is the medium point between alpha and beta. So on any day, on the average, we are selling 100 liters of milk in this dairy farm. The variance of the daily demand is calculated as beta minus alpha to the power 2 divided by 12. And in this case, beta minus alpha is 100. The squared term is going to be equal to 10,000 divided by 12. And you are going to get 833.33. So we have calculated all of this. So before moving forward, let us go back and read the last part again. It says, it is known that today's milk demand was no more than 110 liters. So we know that there is a partial information about today's demand. This partial information says that the daily demand today is not more than 110 liters. So we are basically limiting ourselves in a small portion of the random variables domain with this partial information. So there is this conditional information, this partial information. So given this conditional information, we are going to calculate the probability that the daily demand on that day is less than 85 liters. So we express this solution like this, a conditional probability. So in the end of the day, the information that is given us states that our random variable was less than 110 liters. So under these conditions, what is the probability that our random variable is greater than 85 liters? sorry, actually the question is stating the probability that it was more than 85 liters. Maybe I have misspelled it, but the expression here in the solution is exactly the same as the question provides. So given that the daily demand is less than 110 liters, what is the probability that it is more than 85 liters? Now, in order to answer such a conditional probability, remember now, we were expressing this conditional probability as a ratio. And in the numerator, we were writing the probability of the intersection of these two events. And in the denominator, we were writing the probability of the event given as an information. So in the denominator, the intersection of these two events states what? The random variable being greater than 85 and the random variable being less than 110. And their intersection is going to be the event of the random variable being between 85 and 110 exactly. And this probability then again can be computed by using the differences of CDF values at these points at 110 and 85. So the CDF function x minus alpha divided by beta minus alpha can be computed by plugging in these two values respectively, and the difference is going to be 25 over 100. And the information given, the partial information given, will have the probability of CDF value at 110. Okay, the probability that our random variable being less than 110 and 10 is simply the CDF value at 110. And it is going to be 6 over 100. So the division will yield you a 5 over 12. So please be careful in solving such conditional probabilities. The question does not ask a probability directly. It gives you a partial information, and the partial information must be considered in the probability statements.